My name is Carlos Bustamante, and my laboratory is interested in understanding the mechanisms of control of gene expression. And we like to do this using methods of single molecule manipulation. In particular, we have been interested in answering the question, what happens when an RNA polymerase molecule meets and encounters a nucleosome? And we want to answer this question by describing the complex dynamic that ensues upon this encounter. As you know, the nucleosome represents a fluctuating mechanical barrier to transcription, and as such, it is a general regulator of gene expression. Using optical tweezers, we have recently followed in real-time transcription by single molecules of RNA polymerase as they transcribe DNA that contain nucleosomes. We have characterized how each nucleosomal element, namely the histone tails, the specific histone DNA contacts near the diad, and the DNA sequence being transcribed, contribute to the strength and the spatial distribution of the nucleosomal barrier.
Our lab has previously shown that eukaryotic RNA polymerase has a great tendency to pause and backtrack. During backtracking, the entire transcription bubble moves upstream, and the 3' end of the RNA transcript gets displaced from the active site. The polymerase diffuses back and forth along the DNA template until the active site realigns with the 3' end of the RNA transcript. Then, the enzyme can continue transcribing the DNA.
In the presence of the nucleosome, the downstream DNA is wrapped around the octamer and blocks the enzyme's access to DNA. Therefore, Pol II can only move forward when the DNA unwraps from the histone octamer. As a result, when Pol II meets the nucleosome, it tends to pause more often. Moreover, the nucleosome can rewrap in front of the backtracked Pol II, and as a consequence, its pauses become much longer. As Pol II transcribes the DNA, the nascent RNA product can form secondary structure behind the polymerase. These structures limit backward diffusion of the enzyme and can help it overcome the nucleosomal barrier. During our analysis of the dynamics of single polymerases, we found 3 functional regions in the nucleosome: entry, central, and exit. The 3 elements of the nucleosomal barrier, the tails, the specific contacts, and the sequence, affect these regions differently. The template sequence affects all 3 regions through that RNA structure as mentioned before.
The tails gate the entry into the nucleosome by controlling the unwrapping and rewrapping rate of the DNA associated with the entry region. Removal of the tails favors progression of RNA polymerase II into the entry region of the nucleosome. Macacetylation of biologically important lysine residues in the tails also decreases the barrier to transcription, although to a smaller extent. The small effect of macacetylation on transcription suggests that in vivo, acetylation of these residues, rather than acting as a main attenuator of transcription, probably modulates internucleosomal interactions or creates targets for binding of chromatin remodeling factors. In contrast, point mutation in the histones H3 and H4 that disrupt histone DNA contacts near the diad completely abolish the barrier to transcription in the central region. This result is surprising if one considers that these mutations involve a single amino acid change. The DNA contacts with the globular domains of the histones are very important for the stability of the nucleosome, and thus for the barrier it poses to transcription elongation. We speculate that there must exist chromatin remodeling factors or transcription factors that bind to the nucleosome and specifically disrupt these contact points near the diad to allow access to the nucleosomal DNA to either RNA polymerase II or other DNA translocating motors.
So, the picture that emerges out of these studies is the existence of discrete control points in the nucleosome that can be tuned by transcription factors or remodeling factors in order to modulate transcription through the nucleosome.